so many messages, repeated messages you are sending. I said your report should be, abstract should be in Word document. Okay, and it should have a schematic or if not schematic, at least a block diagram or circuit diagram I was telling. And the same question was repeatedly asked. But your folders, you need to write, I was telling. You need to write the folders. As you are doing an exam, you'll be writing and you'll be taking the snap and convert that into PDF and submit it. Don't get unnecessary confusions and don't try to mingle up the things now. Okay, your abstract should be Word document. Your folder report should be handwritten, converted to PDF. Is this clear? Don't send me the repeated queries saying what to write, what not to write.
Ma'am, is that like diagram mandatory, ma'am, or else?
Definitely. Without that, how you will be supporting that abstract?
Okay.
The complexity of the design can be assessed. It depends now how many segments you are having and what is the flow sort of thing. Everything will be explained in your circuit. Little bit in your abstract, what you are mentioning will be the verbal description, which won't be covering in depth, but the circuit covers in depth. Circuit or your flow. Okay. So, are there any questions regarding your previous approaches? What were seen in the earlier hours? I think we have seen something like what are the ASM synthesis methods, and in that, I think we have seen 3 approaches: traditional, Mux method, and one hot. If any queries are there, you can ask. You have IC applications subject this semester?
No, ma'am, I think it's in 3-1.
Third year. Okay.
Yes,
Some ICs regarding your gates has to be found out now. Okay, what are the specific ICs? Using that, how we'll be implementing these digital designs? Something like an element of D flip-flop, if you take, it is 74 LS175. This is D flip-flop. Quad. What is the meaning of quad? You will be having 4 D flip-flops. So using one IC, 4 states you can implement. Maybe if it is one hot, if you are taking hot method. What is the relation like in traditional method? Mux method and one hot if you are taking. Wrong we didn't take so far. Let us compare this. Like here, how many number of states or how many flip-flops are there? States versus flip-flop. In traditional approach, how many states and how many flip-flops? You should be having this idea fixed now. what is that we are trying to refine is this portion. This is the portion what we are refining. Okay. Why? What is the difference between this and this, like this segment to this segment? What is this segment? What is this segment?
One is controller, another one is hardware.
Which one is controller? Which one is hardware?
Memory. Flip-flops are controller.
This is your architecture. This is your algorithm. Or what you say, this is controller portion, this is hardware. This is your controller. So what are the things you need to give a systematic control signal is the status of the architecture that will be issuing the control signals. So we need to refine this, and this refining depends on what you say, the approach you are taking or the complexity of the design, how many states you have, or how many control signals you have. All this, like based on that, we can change this segment. We can control this segment accordingly. Like in your traditional method, what is that we fix here is, if number of states you take it as n, number of flip-flops is m. What is the relation between n and m?
Power m is equals to n.
2 power m.
Yes, ma'am. Like number of flip-flops is equals to number of state variables.
Like number of states, if you are taking here, we need to take say p is the state variable, say. Something like how many number of p's will be taken will be 2 power p should be greater than or equal to the number of states in the flip-flops, sorry, in the ASM. Number of states in the ASM. Now this P can be related to number of flip-flops. P and M can be related. They are equal. Yes or no?
Yes, ma'am.
M will be equal to P. That means that number of flip-flops needed will be equal to the number of state variables you are having. That is in traditional method. And what was the advantage of this method? Something like don't cares, or like state variables not used, state variable combination not used, or the other way, test conditions, test variables not tested. Can be like this, we can have the state variables that are not used and test variables that are not tested.
Can you
This
record this?
becomes in a segment that can be taken as don't cares. That means the size of the table is a little bit, you can have the reduction. And what is the major disadvantage?
For any
Making-
minute change, we need to change the entire design.
Yeah. Minor changes needs new table or new derivation of the whole ASM. That is one disadvantage. So to overcome this, the Mux method is taken, which is a, yeah.
Meet recording, ma'am. It's not starting.
So this is lookup table sort of thing. Again here, do you have the same relation of the flip-flops versus the number of states? What is the number of, what are the, like how many number of states you have, how many number of state variables you have, and what is the relation, like in this lookup table? Is there any reduction of the elements what we have considered here? Maybe this, to overcome this drawback that your traditional approach had, we are not taking this D flip-flops as it is. That means this flip-flops will be added with multiplexers. Now, what is the size of multiplexer you are taking will be depending on number of states
variables.
or number of states or state variables. How many they are, that decides the size of mux. Okay, and each mux will have one flip-flop, that is your D flip-flop by default, and this size is giving us some flexibility. Like here we said any minute change we need to do the stable evaluation afresh, but here what is the size, how many number of inputs you are taking? If all inputs are used, then maybe you need a bigger size mux or higher level mux. Say if 4:1 is not sufficient, maybe we go for 8:1. If that is not sufficient, maybe combine 4:2 or 2:4:2 or 3:4:2 or 8:2. Something like higher level we will be thinking of to handle the number of what you say the states you are having, because each input corresponds to a state. Each input of the mux corresponds to the state. So this selection lines are equal to, or what you say, this selection lines, I can take this as
number of state variables.
that means P. I'm generalizing that now. So P.
Yes, ma'am. P.
So how many number of state variables you have? That is decided by number of states, and that number of states will be the inputs of your mux, and the state variables will be your selection lines. Now, here we have the flexibility of adding many other states to the unused inputs in the mux. But the size of the mux, what is available commercially, that is limiting us for the mux approach. Maybe we said 32 states, not more than that. That 32 itself is a bigger complex design when you take it as an ASM. 32 states, if you have in your ASM, that itself is the biggest complex design. So maybe mux method is most used method. Not only that, we have one more method. These two are competitors now. Actually, mux and one hot are the most prominently used, but only the hitch what we have in this one hot is, here we are not taking the number of state variables, rather directly the number of flip-flops will be equal to the number of states. Here the cost of the design will be little bit more compared to these two methods, because the flip-flops are directly related to your number of states. Here if you had 4 states, 2 are enough. But here 4 state means 4 D flip-flops are needed. So the more the number of states, the more the number of the flip-flops, maybe that increases the little bit complexity and the cost also. And what is the disadvantage we were having in this one hot? First is the initial state. It should be by default, maybe we name this as PQRS or something. Say state 1 is the first state, it should start from that state, initial state. That means initializing is one drawback here. If you are not properly initializing the design, for every step or for every clock or for every iteration, your output of the design will be different. It's not the wanted output. Can be a valid output, but not a wanted output. Valid in the sense, say you have 4 states. If you start by default at any of S2, S3, or S4 rather than S1, for the next clock based on the conditions, based on the present condition, it will derive what will be the next value. Because these are all linked up. In your one hot, once you start, the next state will be automatically generated based on the present state and the present input that is available to the design at that moment of the clock. So another issue is that like stopping the iteration. Stopping means to terminate. What is the method or what is the approach or facility what we have? Can your machine stop by itself if we are using one hot? It is not possible. You have to use what you say, the universal clear signal. That means synchronous clear. Synchronous reset or clear should be used in order to stop the iterations. Okay, and maybe if these two are taken care of, you can go for one hot in a error-free format. Okay, so these were the 3 approaches what we have seen. The next approach is using a memory, a ROM-based approach. What is this approach is, if you remember, what will be the format of ROM, how you will be using a memory here, what is that needed as the input and what is that output. ROM will be having address lines and what outputs. No? Based on your address, you will be getting the set of outputs, and this we divide that into the outputs of the design and the feedback elements. That means your this one state variable feedback things. That means maybe command outputs we can say, and these command outputs taken back into your flip-flop format. This will be your back thing. I'm taking this as input versus output. The same thing. This is both same, but here in place of this combinational logic, we are trying to use a ROM wherein based on the address that is defined by the combination of input versus the status variables. This defines the complete address. This along with your input and your what you say the status signals will define what is the address of the output. Okay, that defines your total output of the system that will be defined. Like this means this is programmed sort of thing. And as we know that any address line cannot be left vacant. I think this we have seen in the earlier DSD 1 also. ROM and RAM, where if you use any address pin or any address information cannot be left open or undefined. So undefined inputs is not supported by your ROM. Means that you have say 2 state variables and 2 inputs say. Means something like this. 2 inputs, 2 state variables, x0, x1. Maybe I'm naming this as x0, x1, and state variables I'm naming this as a, b, c. Now, what will be the total number of inputs? It is x0, x1, AB put together will be the address. That means here it is combination of sigma of the sum of the state variables and the inputs that defines your table size. Now here in this traditional approach, the same number of two state variables and two inputs if you take, you had a choice of defining some don't cares there, something like the unused state variables or the test variables, we were taking them as don't cares. But here there is no chance of putting it as don't care. You cannot put it as a don't care, rather you have to define all. That means all from 0, 0 to 1, 1, 1. That means 2 power 4, that is 16 combinations you have to define. The size of the table will be 2 power the sum of your M and P's, or something like here. Your P is number of state variables and M is the number of state variables and inputs. I's input. Okay. So here you need to define the total table, and there is no way you can define or you can leave the combination. There is only one drawback here. But if you have patience enough to define this table completely, this is the simplest way of implementing ASM, because nothing is needed to design here. ROM is like you are defining the address location, and in that address location it is already stored in data that will be taken out according to the combination of inputs. But whereas here we need to define the hardware here. ROM is simplest, but only the time taking issue is defining the table. So how we will be taking this? Say, let me take one simple ASM. Taking the simple ASM so that just for understanding this one ROM based method. Pitfalls. How many number of state variables are needed? Here we have 4 states, P, Q, R. Don't get confused with the P earlier defined there. So AB, if you take 0, 0, 0, 1, 1, 1, 1, 0 sort of thing. What will be the size? Here, how many test variables you have? X, Y, 2. How many state variables? 2. So this is something like we need to define AB, X and Y. This is ROM based we are taking, along with what are the new values of A that will be taken to a D flip-flop, new value of B be taken to D flip-flop, and I'm mentioning outputs. Say out 1, out 2, 3 and 4. Okay, now can you correlate this thing, this table with this now? See here. This diagram is relating to like here out 1, 2, 3, 4 will be the outputs here. Okay, and here AB is the new value of AB that will be given to your D flip flop. Okay, what decides the new value is the combination of your previous status values of AB with the present value of inputs. So this is the combination we define. So for every set of the present status and the present input, we'll define the new values of ABs and what are the outputs that will be generated. So complete information will be there in this table now. Okay. So, okay. Let us start with 0, 0. Now, what is the condition? Like in your traditional method, in this path of 0, 0, y is not used. So y was taken as don't care. But here, if you use it or not, must ensure that y also has to be defined. So it will be 0, 0. A combination of all the values is needed. 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. That means in this state. And 0, 1, here in this path, both x and y are not tested, but still we need to define what will be the new value of the AB if x and y are 0, 0, 0, 1, 1, 0, 1, 1. Same way, if you take 1, 0, in this path, neither of x nor y is getting tested, but still we need to define. Okay. And in state 1, 1, y is the parameter or the test variable for which we are testing. X is not getting tested, or x is not a test variable in that path, but still we need to find. So now be cautious here, like how we'll be defining these values of AB, new AB and outputs. 0, 0 state, x is 0, y is not tested, but still we are defining it. And what will be the next value of A, D is 1, 1, because that goes to what you say state 1, 1. And what is the output that will be given is out 1 alone. Right? In this clock,
In that clock, only out one will be coming.
only the stable output or unconditional output defined here is out 1. Out 3 happens for the next clock. Okay, if that is clear, writing this is simple now. X is 0 as it is, y is either 0 or 1. The next state will be 1, 1. Out 1 is the. Now x is 1, y is either 0 or 1. Next value of AB is 0, 1.
Ma'am,
And
you just repeat the first one, ma'am.
this one. State P, that means AB is 0, 0. AB is 0, 0. Why? Whether it is 0 or 1, because this is not tested. X is the parameter on which the next new value of AB is defined. Okay. So when X is false and X is true, we have two combinations here. X is false and X is true. Whether Y is 0, 1 or 0, 1. Okay. In the state of 0, 0. If X is false, that means this condition, X is false, the new value of AB is 1, 1. So 1, 1 we have filled. And output 1 will be generated. Okay, so out 1 only is 1. Out 2, 3 and 4 are zeros. And in the same AB of 0, 0 P state, when X is true, next value is 0, 1. 0, 1. Out 1 will be generated. So out 1 is 1. The same way here also 0, 1. Out 1 is generated. Now next 0, 1. This one 0, 1. Neither of x nor y is the test variable in that path. What is the new value of AB is 0, 0. And out 2 will be generated. The situation is same for all the values of 0, 1 state with x is 0 or y is 0 or x is 0, 1, 1, 0, 1, 1 combination. That means whether x and y both are 0 or 1, the new value of AB will be 0, 0, out 2 will be generated. So fill the table. This is the only time taking thing, but once you define this, that becomes a simple form of implementation. Simplest form. Next 1 0. 1 0 also the same condition. 1 0 because x, y are not the test variables in this path. The next value of AB will be 0 0. Out 4 is generated. Okay, and see here. This will be same for every combination of your x, y in the state of 1 0. Now for 1 1, y is the test variable we are testing for. X is not there here. X is not the test variable, but still we will be testing it. Now see here, these two will be having one similar output, and these two will be having one similar output because y is the test variable based on your y. Okay, in state of 1 1, the next state will be the same 1 1 if y is false. The next state will be 1 1 if y is false. And what is the output that will be generated? 3. And same thing happens here also. 1 1, x is 1, y is 0. Because x is 0 or 1, y is 0 in the state of 1 1. Next state is 1 1. Output 3 will be generated. Okay. Next, y is 1. Y is 1 in present state of 1 1. Whether x is 0 or 1. The next value of AB will be 1 0. This goes to 1 0. 1 1 goes to 1 0. Generating an out 3. Same thing here also. So cautiously you check out. Only one unconditional output will be there for any of the combination of your input. Only one output, one unconditional output. If conditional output is there, maybe that also will be getting included. But unconditional output only one. Or what? How many outputs you define in this rectangle? That many will be defined. But see here, this implementation is very simple once you define this table completely. There won't be any possibility of reduction, or you cannot visualize this in a less complex or minimized form. Complete table will be there if it is a ROM based. Is this clear?
Yes,
Is this
ma'am.
clear?
Yes,
Yeah.
ma'am.
Yes, ma'am.
So, comparatively, which one you prefer if you are given a choice? Which approach? Normally, if less complex designs where you have this combination, maybe until 2 power 5, the table will be manageable. That means either 2 state variables with the 3 test variables, or 3 state variables with the 2 test variables, or combination of that. Maybe until 2 power 5, the size of 2 power 5, defining the table will be simple and easy. Okay. If more number of states are there, or more number of state test variables are there, maybe we go for the choice of either mux or one hot. More number of states are there, maybe mux can be a best suitable approach. Okay. So it's left to the choice of the designer. Each approach has its own advantage and disadvantage. So we cannot say that this approach I cannot use, or this has disadvantage and this is advantageous. Okay. So this is something related to, based on the ROM size that is available in the market, we try to define or we try to take a ROM approach. What is the maximum size like ROM can be? Maybe this ROM approach, smaller systems or small few number of states system, ROM approach will be preferred. More complex, you need to go for either mux or one hot, we were saying. Even in that mux also 32 states, if it is exceeding, you have to split that. In one hot, if you are taking more number of states are there, your cost of the design will go up. So we may not think of this one hot approach. Okay, so if this is clear, we go for the design pitfalls here. We didn't consider any design considerations. Okay, like in the sense, we were saying that between these any two stable states, there is one clock happening. There is one clock. For every clock, there will be a transition between the two successive stable states. Okay, but here 2 points has to be considered. Like, what are the inputs type, or whether the inputs are happening are synchronous or asynchronous. This we didn't consider. We just said some inputs are there, and based on that input conditions, we are making the transition between the states. And what is the clock? What is the type of clock we are using? What is the type of clock means that something like this. You have here different D flip-flops. Are they synchronous or asynchronous? You have set of D flip-flops, or you have the combination of D flip-flops. Are they synchronous or asynchronous?
Synchronous.
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 There is no information now. We didn't mention, but they need to be synchronous. They need to be synchronous. That is one point, but need to be synchronous means that, see something, if I put, say, 2 D flip-flop system I am taking. Say this is for D of A and this is for D of B. 2 clocks and set of input versus output. What I would like to take here is, okay, clock of A I'm taking and clock of B I'm putting in. Now, ideally these two should be same. Same in the sense, the signal appearing at clock of A and clock of B should be at the same instant. What happens if this is not happening? What happens if this is not happening? That means what are the assumptions we made so far is that the ASMs are synchronous and every change in the input or change in the clock, every change in the input or change in the clock, every element, this is your input side, is happening with respect to some reference signal. What is that reference signal? That is the signal for which is guiding, or what you say, initializing the new values, or what you say, what exact point of activation or consideration your design should take for a new value of input at the states, when should it be sensitized for this new value? Say this is for clock of combinational logic and clock A, clock B. All these are hardwares that have a clock, and this we were assuming that they are having a identical clock signal or reference signal. Now what happens if this is getting deviated, or if your hardware is not having the same clock, or your flip-flops in the path is not having the same clock? This leads to some, what you say, an unwanted responses in the design. Okay, and not only that, if a new clock is applied, what should be the stability of the input? That also we didn't speak. I think this point also we had a discussion earlier also. See, if this is the clock of the system, whenever we are giving a clock active clockage, there should be the sensitization of the inputs that are happening. That is one point. And this clock should be common to all the segments of the design. That is second point. Third point is that whether the inputs are stable at the moment when the clock is applied, can the inputs change at any instant? That means something like synchronous inputs or asynchronous input sort of thing. Stability of the input. Stability of the input. What is this requirement? When the clock is happening, before the clock goes from 0 to 1, there is some time that your input has to be stable. What is that? Setup time. That setup time, there is a small duration before the clock goes from 0 to 1. The input has to be stabilized. And that duration for which before the clock is going to 0 to 1, your input needs to be stabilized is called as setup time. In that setup duration, the input should be invariant, stable. And not only that, the moment your clock goes from 0 to 1, there should be some duration for which the input that is happening should be still stable, and it should hold the same amount of value, or it should be stable for that duration also after the clock age of 0 to 1 is happening. This is what we call it as hold time. So in total, if you take the input stability, is the input should be stable for the duration of setup plus hold time. So this duration, this total duration, your input needs to be stable. Okay. If not, what happens we need to see. If not, there will be some pitfall. These things, the elements what we defined, we call them as design pitfalls. Okay. Now let us see each pitfall one by one. Okay. Now see here. I'm taking this clock A and clock B as different elements. There won't be any issue if clock A and clock B are common. Clock A and clock B are common along with your combinational logic clock. Now what happens is, say something like this. If clock A is faster than clock B, meaning that the clock A is happening earlier than clock B, or these will be some design signals that will be coming from some other sources. Clock generating sources will be different. If the clock A reaching this D flip-flop is faster than the clock B reaching the D flip-flop of B, what happens here is this will be making the new value of A to be sensitized, and since this clock B still is not applied, that means new value, that will hold the old value of the B, and if the total system before the clock A and clock B gets synchronized, or that means a new value of clock B is coming into your D flip-flop, in that time duration, if this combinational logic is very fast enough to iterate a new value of the output that generates, or the output that will be coming out will be because of the old and new value of the ABs. Means that this is faulty. This is faulty. Your output generated should be for both new values of ABs or new values of the inputs that are defined here. When this is getting updated with your new status signals generated here for the previous clock now. If that mismatch is there, then the output generated will be a combination of old and new data, and that becomes a faulty response. So this type of the incorrect values that are getting generated because of the mismatch in the clock speeds or synchronization of clock elements, if it is not there, that we call it as clock skew. The wrong value that is getting generated because of the unsynchronized clocks. It is called as clock skew. Okay. So how to come out of this clock skew? How to come out of this pitfall? This is one pitfall we are saying. How to give a remedy? Think of what can be the probable remedy.
Fasting clock B or slowing clock A?
Or
Can we stop one of the clocks for a small duration, ma'am?
that's equivalent to the D flip-flop. Just now someone has given. No? Making the one which is faster, we can delay it using a D element. But
Decreasing hold time of clock B.
Decreasing, no. This clocks we cannot manipulate. Those are the signals that will be coming from the other sources. Actually, clock generating signals are also different circuits. That circuit we cannot manipulate. Rather, what is that we can do is put a signal or put a clock source that is common to this elements of your combinational logic, clock A and clock B, such that they are reaching at the same time. Because see here, this physically, if you put on the circuit, say if I'm placing like this, see, and say clock source is something here, say this is source of clock, and from this I'm defining clock B and clock A, because these are wiring only, no? So what happens is, if different wire length, if you are putting in, that itself generates a clock skew, because the source is placed a little bit nearby to B flip-flop, and little bit far away to A, and little bit far away to your hardware. That means combinational logic. That means that the clock that is generated will be not synchronously reaching all the elements in the design. So what is the remedy? What we can give is place this source of clock at somewhere in center. If this is my clock source, what are the segments I'm having in the design? I try to place them this format. Something like if this is combinational logic, this is D of A and this is D of B. Each will be having the same wire length. Okay, this is this clock source. Maybe this format we will be able to avoid the clock skew. The other way is that if this clock source is something placed here, isolated, if not possible for centralizing this, you run the clock source such that the length will be equal. If this is wiring, this is one length, second length, and third length, or they are equal wide or equal length wire. This format or this format, you can avoid the clock skew. This is practical aspect. When you are placing that, normally in the PCB layouts, printed circuit board layouts, if this is the allocated space in the layout, the designer should decide where the ICs are placed and in what format the ICs will be fixed and what will be the length of the wire that is connecting the ICs, and along with that the sources. If the maybe sources are put to the extreme ends, these are the ICs if you are taking. What is the length that is connecting the sources and to the external pins? These are your external pins. Your PCB. If you can open your PCBs of any of the gadgets, you can see the copper clad that will be having what you say, the ICs or every component placed in a systematic format such that there won't be any sort of skew coming over. Skew can be because of your clock or because of your inputs or outputs. Skew can be of any sort of source. Okay, so the placing, the wiring, everything will be decided by the designer. Okay, according to the requirement, they will be defining the lengths and connectivities. So the PCB layout designing also one bigger segment you have. These layouts will be defining in such a way that each element will be connected without having the skews generated. And not only that, we don't run the wires which are in parallel. Side by side parallel wires won't be run. If you can see, sorry, any IC you take, there will be some sort of what you say, angular wiring thing format sort of thing you can observe. You can open your any old PCBs of any of the gadgets. You can see the wiring which is not running in parallel, but there will be some angle of inclination so that the EMF induced will be avoided. Okay, so this is one element. Now, the same thing, that means this is the length of the wire that will be eliminating the clock skew if the length of the wire is even. Because through the wire, there will be a delay beside. No? The delay, how much of delay you can expect in the wiring? Every 8 inches of wire will introduce 1 nanosecond of delay. Nanosecond delay. Every 8 inches will introduce 8 inches of wire. Gives 1 nanosecond delay. So think of how many inches you have in the wiring. If that is so, like maintain equal length. That is one remedy you can give. And don't go for gating of the clock. That means someone said that use a flip-flop in between. Someone said, no, when I asked what is the probable remedy, you said between these two, use a flip-flop which will be delaying the faster one. Say if this is fast element, use a D flip-flop so that this will be slow and that element of delay will be matching this point. Like if say 2 nanoseconds of lapse is there, use a D flip-flop of 2 nanoseconds here so that they get synchronized. Now, this gating of clock is it's a bad practice we say. Okay, why? Because it will introduce hazards on the lines. Okay, it will introduce hazards on the lines. And not only that, say another remedy you can suggest is that something like putting a positive edge trigger on negative edge trigger sort of thing. That is also a bad practice. Never use different edge triggered clocks in the same design. We need to take both either positive edge triggered or negative edge triggered, and don't try to use another delay element in the path of the line which is faster compared to the other line. That element of adding a day flip-flop or putting extra circuitry is called as gating of the clock. That gating of the clock has to be avoided. Don't gate the clock. Rather, the remedy is use a centralized source for the clock where the wiring connecting that source to all the segments will be of equal length. Okay. So never try to take, like if say here also, if one is positive edge triggered and another is negative edge triggered, naturally there will be a lapse of half clock signal in the same design. If I'm taking, if this is say positive edge triggered and if this is negative edge triggered thing is there. If this is clock of A and clock of B. What is the lapse you get between these two? What is the lapse? This will be
Half of time period.
Half clock.
Half clock you will be getting. That means this you cannot avoid. No, like the lapse what you get, if you need to synchronize, a natural thing what we think of is using a D flip-flop, but that introduces skew, we are saying. So never use two different edge triggered things. Use either both positive or both negative. That is one remedy. And don't introduce D flip-flops or delay elements in the path of the fast lines. That is another one. Only remedy what we suggest for clock skew is running a centralized source having equal distance to all the segments. Means that equal wiring. There is only one remedy. Okay. Shall we take a break or continue here?
Can you repeat why we cannot use two different types of triggered clocks, ma'am?
Because there is a natural, lapse of half the clock duration for triggering the new input for these two. Say, input is ready for both segments, say. Input is ready for both segments at the same moment. But when this input will be sensitized, we are using the same clock. Clock cannot be two different clocks we use. No, same clock source if you are using. Clock source is same, but this fellow is sensitizing for a clock going to 0 to 1, whereas this segment will be sensitizing for the next one. That means total clock is this. If you take from 0 to 1, your A will be sensitizing the new value of what you say this path, and 1 to 0 transition of clock will be sensitized, or it makes the new input to be sensitized by B. That means there is a lapse of this duration. No? And in this duration, the outputs defined will be for old value of B and new value of A. Yes or no? Inputs are same. Let me be clear. Say new input is happening. This is also new input. Say, let me take this. New input of this, new input of this is ready. When this new input of B will be sensitized when clock is going from 1 to 0. When the new input of on A will be sensitized when clock is going from 0 to 1. That means when this A is sensitizing its new input, B is still holding the old data now.
Yes, ma'am, understood, ma'am.
So what happens is, in this duration, all the outputs that are defined will be the combination of this old and new. That is Q. So a natural thing or a natural remedy, what we suggest is either you make both to be positive trigger or negative trigger. This is regarding the triggering, but regarding the distance that is between A and B also will be giving you two different instance of input sensitization. No? This if it is 8 inches you say, and this is 8 plus of some 4 more inches. So this is 8 inches and this is say 12 inches. This introduces 1 nanosecond. This is 1 plus of extra. So here also the clock skew comes into picture. So never try to put the source at isolated or different what you say length wide positions. Okay, we'll have a break for 5 minutes.
Ma'am, one doubt, ma'am. How does centralized source make the time synchronized for both of the clocks, ma'am? Once, please explain that point.
For both of the clocks in the sense, let me.
Ma'am, we place it at center if only clock A and clock B are of same, no, ma'am.
Both are positive edges. Say if this is source, here B and A, if I can put this way, both are 8 inches, say, or same length, and both are of same edge trigger. Then you will be getting the clock signal at the same moment to your A and B both. You cannot take this one of it as negative edge and one of the clock as positive edge, even if it is central placed. Then also clock skew comes. You cannot take this way. This is one approach we were saying, and say if this source is not in a position to be kept at one center, place it any place and see that in your PCB, you'll be putting all the segments in such a position that the wire that is running or connecting will be of equal length. Say if this is your source and these are your devices, see that the lengths are common, the lengths are same, the wire lengths. Two remedies we are saying, two remedies in the sense, both the signals or all the signals should be of same edge trigger. That is one remedy. The next one is that even if you are taking the same positive edge trigger or negative edge trigger, if the wire lengths are not same, then also there will be a skew. So place the source at a central position or a position or the distance at which it is common to all the devices. Is it okay? Got this clarity?
Yes, ma'am. Ma'am, is the source also an another clock, ma'am? In this case.
No. Source, clock generating source, I'm saying.
Okay, ma'am.
Clock is a signal. No, clock is a signal. This should be generated by some other circuit. No?
Yes, ma'am.
So this is clock source. We are saying this is clock source. Or some reference signal generating device.
Okay, ma'am. Ma'am, so will the clock signal generated by will be greater than A? For example, if A is having much more time, ma'am, it is running faster. A is running faster than B. At what time will the source will generate? Will it be near to A or B?
No. Source is common. Say the condition what we have explained here is if the this one clock A and clock B are different, sources are different. First, when we have taken the pitfall explanation, what we have taken is these two are the two different flip-flops having two different sources, we were saying. And this one of that is faster, the other one is slower. That makes a skew, we were saying. But to come out of that, the source should be common is the remedy we have given.
Okay, ma'am.
After you connect, we see that that source is at equidistance. That point of A being faster and B being slower will be eliminated if the source is at equidistance. No?
Okay, ma'am.
How the clock skew gets generated, for that we have taken isolated a clock A and clock B. Okay, so it should not be isolated. The source should be common to all the components in that single design. That's what we say, na? This system clock we are saying, system clock. What is the meaning of that is, it is the clock that will be common to all the system components. Normally, I'll be telling this now in synchronous or your designs, something connected to system clock we say. System clock means that it is common to all the components in the design. Okay, got the clarification?
Yes, ma'am.
Okay, just 5 minutes break. We'll meet at 11:25.
Okay, ma'am.
Okay, the first design pitfall what we have seen is clock skew. The next is races we need to see. Can clarify this is transition race, and the other one is called as out race. For this, let us consider one ASM. Actually, the race concept, I think we were introduced with the races and cycles. You remember this way? This point of races and cycles. You remember where we have seen this? Able to recollect.
JK flip-flop.
That is race around condition, not that. Races and cycles. Order of changing of state variables introducing something. The state to which it reaches. Order of changing of state variables will decide to which state it goes to now. Whether it is a wanted stable state or unwanted stable state. Remember that? In your state
Ma'am,
tables.
it was seen in asynchronous sequential circuits.
Yes. It was in state table where you had y1, y2 sort of thing, this state variables, the order of changing, whether y1 changing first or y2 changing first. It was introducing a race called as an critical race or non-critical race. You remember that? Critical is when the stable state is going to an unwanted stable state, it is critical. Whether y1 changes first or y2 changes first, your next state to which it goes to is wanted state, it is non-critical. To avoid a critical race, we introduce cycles. All this story we have seen in the asynchronous state tables. Yes or no?
Yes, ma'am.
Why the element of y1, y2 is coming is these inputs happening are asynchronous. It can happen at any moment. So that's why we said whether y1 changing first or y2 changing first, that point has come into picture. So both if they are changing at a moment, maybe there won't be any issue. But if y1 changes a little bit early than y2 or y2 changes a little bit early than y1, that analysis completely we have seen. The same element you put here also. Say we have some state 1, 2, 3 and so on. What is the point we are interested in is say this is an asynchronous input. I'm saying this is an asynchronous input, and based on this asynchronous input, say a conditional output is happening. Say one conditional output is happening, and along with that, say I'm taking this as some true false transition, and 0 1 1 does not take these values. Only the point of interest here is if these inputs that are happening are asynchronous, that means asynchronous inputs and races, there is a relation between this race and the inputs. Okay? Here, for each flip-flop to go from one state to another state, there is a need of change of the state variables to happen, or there is a need of an input change that is needed to make a transition between two stable states. Okay, and say if these inputs are happening at some interval where there is a sufficient time for the outputs to be properly defined or evaluated, then the system is fault free. If the input is changing in such a way that there is some sufficient time given for the system to evaluate a new output, stable output, then your system is fault free. But if the inputs that are happening are very untimely, that means asynchronous, we cannot expect when the input change is happening, or that input change happening is very short duration, say, then also there is a chance of an error output happening. Okay, so here in this path of S2 to S3, if you consider, there is an asynchronous input we are saying here. This asynchronous input, say if this is happening at an interval, say this is between two clocks, one clock and a transition between two states. In a one clock, a transition happening between two states. Okay, and this input is happening at an interval very much near to a clock signal, making a transition of 1 to 0. Actually, this is the duration what we take for iterating the new values or stable values. Actually, that should happen at the beginning of the what you say transition of 0 to 1 we were saying. Now, this is asynchronous. This may change at any interval of your clock signal. And if this interval, the change in this input is happening very close to a clock changing from 1 to 0. If this input, which is asynchronous normally that will be indicated with an asterisk onto its top normally. Okay. This, if it is happening at a shorter interval, wherever this is going from 1 to 0, just near to this position, if that input is happening, there is no sufficient time for the system to generate, say, this conditional output. Straight away it is going to another stable state S3. Can we call this as a race? An input changing at a shorter duration before the transition of your clock going from 1 to 0, or before the transition of S2 to S3. The input happening is very abrupt, and that we call it as a runt pulse. Actually, runt pulse means that it is a very shorter duration, and that too that is happening at the instant of a transition of clock 1 to 0. That means clock is going from active on to off. Before that duration is not sufficient for some other iterations to be complete. Maybe your system will be landing into a new stable state, because this is the iteration path, and within this we are saying before the clock goes from 1 to 0, it has to complete that iteration. So by nature, this iteration will be complete and makes the system to go from S2 to S3, but because of the shorter runt pulse type of input, asynchronous input happening, it is not giving a sufficient time to evaluate some conditional output. That means there is a chance that before generating the conditional output, it may land into a stable state, but skipping some outputs that are supposed to be evaluated. That type of error response, we call it as an output race. Output is not getting generated because of the run pulse. Okay, and this is the direct result that your ASM output being a conditional output, which is dependent on asynchronous input, Okay, this element, we call it as an error condition. That means we can have asynchronous input, but until what extent we can bear that asynchronous element is that it is not in a shorter duration, but it should have some sufficient time given for the system to evaluate all the outputs, including the conditional outputs and unconditional outputs also. Okay, so maybe what can be the possible remedy for this type of runt pulses that are happening is that make all the asynchronous inputs happening to be synchronous with the system. How can we do that? Make all the asynchronous inputs to synchronous elements. That means make them synchronized with the total overall design elements. How that can be happened? What is the remedy? Anywhere you see an asynchronous input, run that through a D flip-flop so that this will be synchronized. This becomes synchronous input. Now apply this input here rather than putting this as asynchronous. Synchronize that through a D flip-flop. Then that input, you can use that into your design so that there won't be any output raise happening. Why we can call this as an asynchronous input is this is with respect to the system clock we are using. We run this flip-flop with reference to the system clock. That synchronizes the asynchronous input happening to be synchronized or to be appearing at the moment of the clock happening from 0 to 1. This will be synchronized with the other elements of the design. Why this race is dangerous sort of thing? We say if this is design is something a conditional output sort of thing, an alarm, okay, a theft alarm sort of thing. If you visualize, an input is happening, a sensor input. Say if this is a sensor you are giving, an asynchronous input is sensitized. That means the theft is done or a thief is entering. And that moment where the thief enters is synchronous or asynchronous. We cannot visualize that as synchronous. No. Any moment an input is happening, a theft is happening. Maybe your sensor should sensitize that and it should generate an alarm signal. Then it has to go to some other state, say. But this alarming signal is happening as a run to pulse. That means very shorter duration before the clock going from 1 to 0, it is happening. Instead of generating an alarm, it may directly go to another state without generating alarm or without alarming out. It may go to another state. That means a signal what is supposed to be cautioned is ignored. That is faulty. Or else say switching on or off or door lock or open system sort of thing is there. Okay. Before something like it is closed, this is closed state and this is open state, say. A door open and close. A person if not entering at equal intervals, that will be taken as asynchronous. At equal intervals, if it is there, okay, no problem. Between these two states, that the event will happen. If a person is entering a moment before closing, what happens? the person is half the way in the door, it closes, which is dangerous, no? This command output should issue a command saying open the door until this total duration what is prescribed, and then it has to close. If a person is entering asynchronously at some interval where the clock is going from 1 to 0, just before that, before he crosses the door, if it closes abruptly, that is dangerous, no? It's one example we can take. So there should be some element which can be monitored, or what you say, asynchronous inputs has to be monitored and synchronized. That is the only remedy we can give for an output race. If that is happening because of the asynchronous inputs happening. Now this one, see here, say I take this as 1 0. Let me take, just for explanation I'm taking. See here, I'm giving an AB value as 0 1. It needs to go to a 1 0 transition. That means two variables needs to be changed in order to have state 2 to state 3 transition. Two state variables are involved and two state variables needs to be changed. Okay. Now, if these state variables, changing of state variables, it depends on the order of changing. This is as if the same thing, your critical race. Critical race. Okay. The input happening is not having sufficient time. That means asynchronously that is happening. Instead of making that, say if this is happening as true, if it is not giving some sufficient time for the output, new output to be generated, what is to be going from 0 to 1 to 1 0, it may land back into 0 1 itself. Or if A and B are differently unsynchronized, A and B are unsynchronized. A can happen at any instant, B can happen at any instant. This 0 1 can go to 1 0 or 1 1 or 0 0. It's not predictable. So this situation where the next state depends on the exact timing of the change of the flip-flops, because we are speaking this in terms of change of flip-flops only. No, each state variable will be fed to one flip-flop. Each variable will be taken through one flip-flop. In our ASM synthesis, we have seen. So, if the next state value depends upon the exact timing of the change of the flip-flop inputs, the change of the order of changing of these flip-flop values, that is called as transition race. That is called as transition race. So the races what we are taking in the design elements is that asynchronous inputs happening and the order of changing of the variables happening if they are either run or what you say abrupt changes. Then we have the races called as transition race and output race. So what is the remedy that you can suggest for these elements are synchronizing all the asynchronous inputs wherever you have in the ASM or wherever you have in the design. Okay, that means what are the elements what we need to consider here is the inputs that are coming into your design should be glitch free. Glitch free. Glitch means it should not be having an abrupt change. This we call as glitch. If this is our total duration of any abrupt change, we call them as glitch. It should be clean and glitch free, we are saying. And wherever you have any unexpected or asynchronous inputs happening, try to synchronize them using one extra circuitry of D flip-flop. One extra circuitry of D flip-flop, or else the debugging of asynchronous designs becomes very difficult. Debugging of asynchronous designs is very difficult. Always a designer thinks of converting all asynchronous inputs or asynchronous design elements to be synchronized. There is only one remedy that will be suggested for a fault-free designs. So in total, if you can conclude, you need all these assumptions or whatever, like so many things we were saying, na? Have a clock skew sort of thing, or you have some asynchronous inputs happening. So all these assumptions, whenever we someone has unmuted. Akshit Sai, mute your mute. Okay. See, whenever a designer takes all the design considerations, designer Akshit Sai, Akshit Sai, logged in through two devices, mute yourself. So for a Sai Varun or Dheeraj,
Yes, ma'am.
call Akshit Sai and ask him to unmute. He logged into the two devices and both are unmuted. Okay, so the conclusions of our designs is that the designer design considerations, whatever the assumptions that are made by the designer, he himself will be forgetting a specific design points when he visits back at the later time. See, what the design today we do, we ourselves will forget what were the design considerations we have taken while designing. So the best thing is we need to document all the design considerations or design parameters, what are the assumptions we have done, or what were the inputs that were considered, how that was like defined while connecting and all. All this becomes the documented things, like what we say manual. We need to document our design considerations. Okay, and never attempt any design of high complex things as one single entity. See that your designs are modular. Modular in the sense, at least some designs that like the complexity is can be handled very simple, easily. Modular means something like not total less complex, but the complexity should be little bit manageable, we say. Designs should be modular. It should not be very big or very small. It should be at least moderate enough so that you can handle it and the maintenance engineer will be in a position to handle it properly. Okay. That means not only that, whenever we need to repair the design at a later moment, it is not the designer who repairs, it is the maintenance people that who will be repairing. So for a maintenance engineer or a maintenance person, he needs the document or what you say the manual at the later moment. Whenever we are taking our gadgets to repair, okay, um, like first of all, that maintenance engineer should be having the total knowledge of that design. First of all, if he needs to repair or at least analyze where the fault happened, yes or no? So who will be the person who gives all the information? Not the designer will come to every maintenance engineer. So it should be universally distributed manual that should be available for each design. So that's what we call it as documenting the design, which will be distributed or stored as a manual. And the modular aspect is that any segment should be in a position to be replaced or repaired. Any segment should be in a position to be replaced or repaired. That can be done if the design complexity is not so huge that even your maintenance engineer will not be in a position to identify or repair the things. It should be modular enough. Okay. And the other thing is that whenever we are designing, we should not think of about the outputs that are to be fault free for this moment. Okay. The design should be in a position to be giving error-free output forever. Means that few designers has this in mind. So something like at this moment, I want to come out of this situation. So I want to use some trick, some trial and error sort of thing. And for that moment, if I get an output satisfied, I leave that. No, that sort of designs won't exist in the market. The design what the designer what you say assumptions or considerations that are taken into the design should be trick free. It should not be what you say temporary solutions. It should be a permanent solution. Some error is happening, don't think of a temporary solution to that error, rather think of giving or providing a permanent solution. Then only the design will be a successful design. Okay, the same thing for when you are releasing your designs into the market. Your design should be existing in the market for longer duration, means its performance should be sustained. Its performance should be continuously giving the same efficiency. Performance should not be degraded. So never use any tricks while you are designing your designs. Okay, so uh, so what are the total design guidelines? Can you list out from whatever we have said now? Design guidelines. From first hour, we were seeing all the designs, no? Top-down approach. Sorry. So the first step is when you have begun, we said prefer top-down approach. Before ASMs, these were the points we have seen. Na? Clear cut, what you say, classification of architecture and algorithm. Third one is linking of your architecture and algorithm. Is it proper or not? Okay. If not, you redefine the classification. Instead of like thinking of some remedies here, you directly go back and redefine the architecture and algorithm in another way. Okay, the classification you can classify until a satisfied result is achieved. Okay, and when you are classifying, or what you say, separating this architecture and algorithm, the separation should be meaningful. Meaningful in the sense, there should be a proper relation between the algorithm and architecture. There should be a mutual, what you say, control of the algorithm and architecture over each other in order to have higher efficiency. That means 100% efficiency. Towards 100%, if you want to achieve, redefining the architecture and algorithm is the best approach. That means maybe first time you classify based on your first step of identification, or what you say, understanding of the problem statement. Do the what you say, take your CAD tools, you try to what you say, simulate, see the result. If the result is not satisfying, come back again, you reclassify that. Separate the architecture and algorithm, and the how many times you try to redefine this is until you get a satisfied result in your simulation. We don't, until that we don't go for hardware. Okay, we don't go for hardware implementation. Prototypes we don't develop. We try to use this step using the CAD tools. Okay, so this is your basic approach. So I'm giving the design guidelines, conclusions. Okay, design guidelines. The other technical point is, technical considerations is that what we said just now, clocks should be synchronous clocks. Use synchronous clocks in your designs. Next one, what we said, input should be synchronous. That means avoid asynchronous inputs. Inputs should be synchronous, clocks should be synchronous. Another one more point we forgot to mention here is, see, here we are saying clock as one, sorry. Here this clock we are giving some on-off time, no? Your system should be operating with same efficiency with whatever the clock speed you are giving. It can be having a 0 clock speed to any amount of clock duration. Your system response should be free of all these pitfalls. That means you make your system to be static. That means it should be independent of clock. Whether this of 20 nanoseconds or 0 nanoseconds or 100 nanoseconds, your system response should be same. Your designs then are said to be static. they are said to be static. Okay, the last point what I have given is the design philosophy. If you take design philosophy, just now what we said here, documentation should be given, and the second one is the designs should be simple and modular. Why? What is the reason for this modularity? Documentation for understanding at later moment also, and for maintenance. This designs should be simple and modular for easy repair and maintenance. Okay, this documentation will be used by the maintenance engineer and the repairing person, and the designer himself will not be able to identify his own design at the later moment. So a documentation comes to the rescue. Okay, so every design should be documented. It should be simple and modular. You should not use any tricks in your designs. It should be clean of tricks. Okay, think of a permanent remedies for whatever the pitfalls you have, rather than going for some temporary adjustments to your designs. That is the meaning of no tricks. So this completes the total, what you say, the design as per the specifications and as per the what you say, design standards. These are the points what we have seen for these many hours. Okay, what is the base approach for your design, and next is how you have to handle your inputs, and what are the ways you need to like achieve the what you say, error-free output designs. This completes one basic level of designing. This completes one basic level of designing. So I request you to take any textbook and try to evaluate the ASMs in all the 4 types of approaches, 4 synthesis approaches, and try to get the clarification of doubts. Like if that is properly understood, then we can go for practicing the designs. If any doubts are there regarding the design considerations and all, you can get it clarified now. And take any textbook, maybe this Prosser and Winkler Roth also, they give the ASMs, take the exercise problems and work out in the 4 styles of modeling. And trying to see that you are at ease in defining all the what you say, your one hot approach designs or mux designs or ROM based designs properly. Okay. So next hour I'll be taking the designs and VHDL. Anyone has started reading VHDL?
VHDL, no, ma'am. Verilog, we are practicing.
Verilog you have started.
Yes, ma'am.
So VHDL, any like you need VHDL introduction sort of thing?
Yes, ma'am.
Okay. So basic difference, you need to first learn about this VHDL and Verilog. Then writing them will be very simple. Either you take Verilog HDL or VHDL. Both means the hardware description language alone. Okay. And your Verilog aspect is little bit simple compared to VHDL, but both addresses the same length of designs. The hardware description is to the same extent. Something like say, maybe let's take this. So this VHDL, let me introduce this hour, and next hour I'll take this VHDL. So this V here stands for very high speed integrated circuit hardware descriptive language. That means we are not handling small scale integration or medium scale integration. Okay, the level of integration, it can handle any level of integration, but we try to write something right from large scale integration here. Okay, actually, this is the um, combination of some languages, we can say, for some sequential language, concurrent language, and it will generate the netlist, and this is netlist language, and it gives the timing specifications. What else it can do is waveform generation language. So all these languages put together is nothing but VHDL. So it can be thought of an integration of the languages of sequential addressing or concurrent statements. Netlist means number of input versus output sort of thing, and timing specifications is you give the inputs to like you specify the input, and with respect to time, what are the variations in the outputs will be defined. That along with your waveforms you can analyze. Okay, all this put together is your VHDL, and actually this is what we say is in standard of IEEE. What is this IEEE standard actually is something like a programmer or a designer who is designing for his design that can be considered into others' designs. Something like, say, a design what I design and a design what you design can be like, if this is, say, I named it design 1 and your design is design 2, a third person can take these two designs into his design. That means there is a concept of what is called as portability. There is no fast restrictions that are put on to the designs now. Anyone can use any design of others into their designs. That means it's not that any feeble design that is there in the market can be taken into your design. No, there should be some standard. If that my design is to that standard, so there is an organization or there is a what you say, an entity which can fix the standard. To that standard, if my design is, then that can be floated into the library of the design so that anyone can use it. Okay, so what is that standard is what we call it as ANSI standard. You know what is that ANSI? American National Standards Institute, ANSI standard. Okay, and all the elements that are defined. Okay, now this we are saying as something in portability. The design should be according to the rules of IEEE, ANSI standard, and they should be application specific integrated circuit. So all your VHDL, whatever you are mentioning, will be to these standards. Okay, if these standards are like achieved to that level, your design is, then your design will be ready for portability. This can happen when you are properly compiling and simulating the design, and your design is perfectly working. Then that will be transferable to some other designs. So the standard will be fixing, or where we try to see all the fixed standard designs is uh, this IEEE STD logic visit. This is the library where it will be stored in, and from there we will be trying to take the designs. Okay, from the beginning, many different standards were started, and now the standard what is available at in the year 1993 until that it is 1164 standard. Now latest we need to verify, but this is sufficient enough for the student to import the designs, exporting and importing the designs. Okay, so based on these standards, okay, what are the capabilities of writing is very difficult on this pad. Okay, what are the capabilities of this VHDL language? Is that you can simulate or compile using any standard CAD tool. What are the CAD tools available for
CAD tool,
what are the CAD tools? What are the tools you are using now?
Xilinx, Ieee.
Xilinx, have Altera. Earlier we used to have Max Plus. All this, like we have plenty number of CAD tools, and the tool and the what you say vendor. Your VHDL will be the mediator between the tool and the vendor. So that means something like a designer, that means a vendor or a designer will be giving the specifications. What should be the design to be looking like? That means some verbal description. Whatever we were saying so far as a verbal description, that details will be given by the vendor or the user or the designer, not the designer, vendor or the user. And this VHDL will be like writing a story based on the vendor's description. Your VHDL is nothing but a story writing sort of thing. It's very simple. You understand the problem statement, you are writing the story, that story relates the inputs and outputs, that's all. It's as simple as that. And now the tool will be doing what you say software simulation rather than a hardware implementation. Directly putting it on hardware and damaging the things, it is a better platform where you will be simulating and seeing the system performance based on how you are writing the the program. What is the expected output that you can visualize, that you can try to simulate and see what exactly will be the output of the design when physically it is formulated. Okay, that means you are trying to see the behavior of your design before going for the physical thing. That means functional simulation will do. Functional simulation you will be doing. How your design behaves for the combination of inputs, that can be evaluated. The functional simulation can be done. Okay, so this becomes a communication media. Your VHDL programming becomes a communication media between your CAD and CAE tools, CAD and CAE tools. Okay, and not only that, this VHDLs has some hierarchy. That means it follows the set of interconnected components, and each component will be modeled as a subset of components. Something like this one. Hierarchy means if this is my major design, okay, it can be designed as, say, top down. I cut that into some smaller segments, and this segment again, if I take, if this is D1, again this I can cut into some other smaller segments. That means this become the subsegments. These are the subsegments for this D1. D1 will be subsegment for my D3. That means it follows the interconnected components. You can define that as interconnected components. It supports that connectivity. Any lower level designs, you can connect them to form a higher level. That is as simple as that. It supports the hierarchy. And this supports both, not only top down, it can be implemented in bottom up or mixed style. Any style of modeling you can take. That is the flexibility you have in the HDL. Okay, like it is not what you say technology specific sort of thing. You can integrate various level of hardwares. You can develop your own components. It's not that every component should be there in library. Anything, any idea coming onto your mind, you can formulate that into a design. Okay, you're not putting that on hardware, rather you are putting that on a software simulation. It is safe for you to what you say, formulate the design and try to see what are the outputs you will be getting or how your system will be once it is coming as a physical design. That sort of what you say, designing or evolving new designs can be happening using the HDL. Okay, and what other types it can support is that both synchronous and asynchronous type of inputs you can give. Both synchronous and asynchronous type of inputs you can give. And you can define FSMs. Okay, you can define ASMs, and you can define simple Boolean equations. Anything, any level of complexity you can write using VHDL. There is no limitation. Complexity is left to the ability of the designer. Any simple equation to a biggest FSM sort of thing also you can write using the descriptions in your VHDL. Okay, and this is something like universally readable format. Any person can read. It is publicly available for every user. There is no restriction, and this is machine readable as well as human readable format. This one, your HDL program, what you are writing, whether it is Verilog or VHDL, they have the accessibility. It can be available to any layman also. If he can understand, he can read it, and he can understand what is the design that was defined there. Okay, and this has something like 3 types of descriptions possible using this. Something like structural element you can write, behavioral element you can write, or data flow element you can write. So this we call it as description styles. Description styles. Any style of modeling you can write the program. You can write the test benches also. Okay, you can write for different delays, 0 delay to some nominal delays, maximum delays you can give. You can put that setup and hold times. Setup or hold times you can define. That means every description, whatever we have seen in the previous DSD1 or DSD2, every design you can put it in your VHDL modeling. Okay, it has back annotations also possible. Something like the information of how much delay you are giving or what type of values you are giving. All that back annotations can be provided in your VHDL. Okay, and the designs can contain information of what you say user defined information also. You can define your own information. not only universally acceptable information, you can define your own information sort of thing. Something like vector type of, say, I name some signal as input. Okay, input A, I say. Who defines what is the type of input? Either you define this as your own specified input, or library specified inputs also. It can be a bit, it can be a vector, it can be a string, user defined. That is possible in this. Okay, new data types also you can define. As I said, not only bit, vector or string, your own data types you can define. Okay, all that should be properly addressed and placed in this standards. Then it will be portable. This will be portable. So, what is the capability of this VHDL is universally implementable, descriptive, or what you say, you can define or collaborate. All these are the things that your VHDL provides. So these elements already we have seen in our designs. This is nothing but the component level. Structural means component level. Behavior means if then else. Data flow means Boolean equations. These things, Boolean equations. All this we have seen in our previous designs, right from day one of the DSD 1 to now. Whatever we have seen, all this will be defined in any one style of modeling. Okay, and how this hardware abstraction can be defined in this VHDL is what we call it as an entity. In your VHDL, it was called as a module. Okay, here each description we name this as entity. The entity is nothing but a design now here, a device design. Okay, now this entity, if you put this, a device is there, some big design or device you are defining, high complexity. If you can handle this as one design, okay, well and good. Directly you will be defining the inputs and outputs and taking the design. If you cannot handle this as simple, you can make or you can divide this into the segments of different sizes. Okay, and we can call them as independent entities. Entity 1, entity 2, entity 3, and so on. Entity n. This can be of any complexity. It can be as simple logic gate sort of thing, or a complex design. Okay, it is something like we are taking this as top down now. You can divide the design into a manageable segment, and that manageable segment again you can define. Say if this I can handle as single design, I define this as entity for top design. If I'm not able to handle this as single design, I can split that into the smaller entities and independent devices, and I can define these entities as what you say, mutually independent designs. Then I can integrate them together to form this major design. That possibility is there in these designs. That possibility is there in these designs. So here each design unit, or what you say, each design entity, if you take, the VHDL program will be giving you 5 different types of primitive constructs. These entities will be defined using 5 primitive constructs. Okay, first one will be the entity declaration. You can relate this entity as module in your Verilog. Okay, that is not different from your Verilog coding. Both are same now. Entity declaration means this won't be defining what is the hardware inside, but it defines only the data, or what you say, the inputs and outputs of the design. Entity declaration declares the number of inputs and outputs of the design. That's all. Okay, and maybe primitive constraints, we can call this as design units also. Okay, first design unit is entity declaration. Second design is architecture body. Third one is configuration body. Fourth one is package declaration. Fifth one is package. Okay, so these are the primitive constructs, or what is it, the design units for either of your VHDL or Verilog. What exactly are these things is something like this, like when you are defining the total design, any design you take, either you take a top design or a sub-segment, each segment is called as an entity, and each entity will be having its own inputs and outputs. This is something like in your full adder, if you take, if this is a bigger entity or top entity, you were defining this as AB and CI minus 1 now. And this will be sum and carry. This is top single top level design. If I take it as a single design, if I can't handle this as a full design, maybe that we were designing using half adders. No? So half adders becomes the subsegments now. And that half adders again, if you take them as an entity, this is entity 1 and say you have an OR gate also no? Inside. So this is one entity, that entity is repeated, this is second entity. So each entity you will be defining separately. Now this is OR entity. And this entity has its own input and output, your AB and sum and carry. Whereas your OR gate, again, if you take say X5, some other names you give, and this is Z. That means, say here, this entity if you take, or the subsequent entities you take, each entity has its own inputs and outputs. Each entity will be having its own inputs and outputs. So that declaration is nothing but your entity declaration, which never speaks of what is the internal hardware. They never speak of the internal hardware or logic. Just the entity declaration declares the number of inputs and outputs. That's all. It gives the information regarding how many inputs you have, how many outputs you have. That's all. And the architecture body is the major thing where it defines about the hardware of the entity. Your architecture body will be defining the total hardware of the entity what you declared here. Okay. Now, in this, the what you say, the description, the total entire description of your design is lying on this architecture body. You will be defining the relation between the inputs and outputs here in the architecture body using what we call it as configuration body, package declaration, and package body. What is configuration body is the configuration declaration will be defining what is the hardware what you are using in the entity design. That means it specifies, say in your architecture body, say you are defining here for full adder A half adder is there. Half adder and OR gate are the entities you are having, say. That is the architecture body of full adder. Half adder and OR gate is the architecture body of full adder. Now the configuration body will be giving what is the relation of this half adder to your full adder and what is the relation of this OR gate to your full adder. That means top level entity, their relation with the components you are using. This becomes the components. That will be declared by the configuration body. Your configuration body will be giving the the connectivities between the components that you are declaring in the entity. And the package body, that package declaration is there. Na? This will be declaring the types of the signals what you are using in interconnecting this. You said OR gate, inputs, outputs, we were defining. Na? Say if you say this as bit, it can be a vector, the value, say if x, y is there. You say in bit, means it is type input and type of the value is bit, that means single value. If I say it is in vector, means it is input type and it can have vector values, that means 0, 0, 0, 0, 0, 1, some set of values. You can declare them. Okay, that declaration is given in package declaration. And package body is the one which defines the definition of the declared element. Defined element. Got this difference now? Package declaration and package body. Package declaration defines the type of the signals or type of the interconnects you are connecting them. And the definition of that will be given by the package body. Understood? So, by default, all these 5 elements will be there when you are writing the HDL program. You will be having the entity or module declaration, and that will be defined by the your hardware that is defined in this entity, or your module will be completely bounded or completely defined in the architecture body. And your architecture body defines the hardware. Entity defines the the netlist that is available for the user. Entity declaration will give only the netlist of the inputs and outputs. This never speaks of what is the hardware internal, and architecture speaks of the hardware. And the configuration body speaks of how this hardware you are defining here are related to each other. And package declaration defines the type of inputs or outputs you are defining in either at the entity level or at the architecture level. And the definition of the declared signals or declared inputs or outputs is given in package body. Package body is nothing but the definitions of the declared signals. Okay, try to understand these points. Try to understand these points now. And based on this, exactly when you put this into the simulator tool, after writing the the HDL programming, by default all these 5 will be incorporated in your language. Okay, and when you are taking this into the tool, you will be doing what is called as compilation and simulation. So the step of compilation is that you will be checking that syntactically whether your writing is proper or whether your declarations are properly connected or any declared signal is not connected, not defined, or it is kept vacant. All this, what you say, the checking will be done by the compiler, the compilation portion. After everything is properly defined, linked, and elaborated, then the netlist will be generated. Okay, and taking that to the simulation level, we will be following these steps. We need to do the elaboration of the signals, whatever the netlist, the compiler generated netlist, we elaborate the values in this stage. Okay, we elaborate all those signals and we try to give the values. Initialization is done in your simulator. Elaborate the netlist in your simulator. This segment, elaborate the netlist generated in your compilation segment, and that netlist will be initialized with values. Then the simulation will be done. These are the stages what completes your total, what you say, designing using tool. So these are the things what you will be using when writing. In the three styles of modeling, you will be doing either top down or bottom up, whatever element you are taking. You will be defining the entity, you will be defining the architecture, you will be defining the configuration that links up, and the type of signals you are using and their definitions. Okay. So in your simulation segment, the elaboration, the initialization, and simulation will be done. It's not just simple simulation and compilation. The compilation is checking of the syntax and generating the netlist. Simulation is elaboration of the netlist and initializing the values, and then simulating, which generates the waveform analysis window. Okay, these are the stages what you have. Maybe tomorrow I'll take up how to write the programs. Okay, so these are the basic introduction of the HDL now. Any doubts you have, or else we'll close this session here.
And I was doubting Verilog.
Your voice is low. Tell.
Actually, in Verilog, I cannot like initiate a 4-input AND gate, ma'am. Like even if I give that all inputs like
4 input and gate.
4-input, ma'am.
Ah.
Like multiple input, single output gates are not like designed, ma'am. Like in that, it's just taking two input gate on and integrating that.
No, there won't be any limitation, no.
Don't know, ma'am.
Number. No. There won't be any limitation. Number of inputs, any number of, say if it is taking 2 means it is multiple only, na.
Yes, ma'am. Actually, like like generally we will be getting only 2 input, 1 output AND gate now, ma'am. I wanted to make 4 input, 1 output AND gate. But whenever I give the code, it is taking like it is using 2 input AND gates and making it the output, ma'am. I asked
That means, yeah, no. You have taken the library functions or your own defined gate.
My own defined gate, ma'am.
Your own defined gate means it has to take. If you are taking that library function means then it will take whatever is already available, that it will integrate. You check it out whether it is, if you are using the same name, whatever is there in the library, maybe by default that will take that library saved gate.
Yes, ma'am. Actually, I asked about this with Aruna ma'am. Ma'am said that whatever you do, like that simulator will take 2 input and get and it will integrate only. So don't worry. So ma'am
No,
is that no.
name, if that name is resembling that in the library, with the same name, some other gate is there. Okay, lower level gate, it will take. Got this? Yeah, you're taking AND gate, say. AND gate is already defined in the library, now.
Yes, ma'am. But
So it will take the lower level and it will take like at the schematic level, it shows the 4 input only, na? 4 input implementation only it will show, na?
no, ma'am. I like generally if I like for example in structural modeling, I initiated a gate, ma'am. Our like one output and 4 inputs I gave to the gate, like and G1 in bracket I gave A comma B comma C comma D comma E. But it is taking two like 2 input AND gates and then integrating it. It's
But
not
ultimately
taking.
it is showing 4 input thing only, na?
No, ma'am. In schematic diagram, I can see 3 2 input AND gates, not 1 4 input AND gate. Instead of
Whatever
4.
it is, no, whatever it is, your functionality is 4 input functionality only, it will be implementing.
Yes, ma'am. Functionality is correct, ma'am. That like output and like thing is correct, but it's just taking only lower level.
Taking a lower level component, it integrates by default. If it
Yes,
is
ma'am.
there available in the tool, that means in your library, it will integrate that. What is user defined to that level only it will show. It will integrate.
Yes, ma'am. That like we
Oh,
cannot
okay.
get like 4 input AND gate at once, ma'am. In schematic diagram, there is no way.
No.
Okay, ma'am.
But functionality, your result is getting correct now.
Yes, ma'am. Result is correct, ma'am. But in the schematic diagram, I cannot get 4 input AND gate.
Integrated option of lower levels you will be getting.
Yes, ma'am.
That's what it will do.
Yes, ma'am. Because like in like when I'm writing the report to
Writing the report logically, theoretical analysis only you write. Theoretical way how you have taken only you write. But Verilog programming thing, your output file will be a normal output, like theoretically how you evaluate the same thing you get. Schematic only you will be seeing that it is lower level integrated design.
yes, ma'am.
So
But
when
we have to describe the circuit, no, ma'am, in
when you are
report.
drawing, write the original way, not the Verilog version.
Okay, ma'am. Diagram also we have to write the theoretical diagram, no, ma'am. Like draw the diagram.
Yes.
Okay, ma'am. Okay, ma'am.
Okay.
Okay, ma'am,
Shall
that's
we close now?
yes,
Okay.
ma'am.